This is the deep outbound track of 3I Atlas, now drifting through the cold outer reaches. Back in May and June of 2025, NASA's TESS satellite recorded the comet already active, nearly 600 million miles out. Standard comet models say water ice can't sublimate at such distances. To maintain a stream of dust pointing toward the sun, the material must be dense enough to push back against the constant pressure of the solar wind. This is where Loeb's estimate comes in. He calculated that the antitail S density must be about 1,000,000 times greater than the surrounding solar wind. No standard comet process can explain such a concentrated, sustained flow. Normally, the solar wind would disperse that material rapidly. Yet, the antitail holds its form, as if locked in place by a force far stronger than simple outgassing. The tails are more than a spectacle. They are a numeric challenge to everything we thought we knew about comets. Avi Loeb's calculation starts with the numbers. To keep 3I Atlas as bright and active as it is, the comet must be losing about 200 tons of material every second. Over the 2 months since it passed the sun, that adds up to billions of tons, roughly 1/10 of the comet's estimated total mass. The expectation is straightforward. At that pace, the comet's nucleus should be shrinking fast or even breaking apart. But that's not what the images show. NASA's Mars Reconnaissance Orbiter captured 3I Atlas as a glowing sphere, its coma stretching nearly 1,000 miles across. Inside that cloud, the solid nucleus is tiny, just a few miles wide with a surface area of only 30 to 40 square miles. Yet Loeb's math says that to sustain the observed outgassing, the comet would need about 620 square miles of actively sublimating ice. But even high-resolution images show a single, intact nucleus. No fragments, no spreading debris cloud. The comet's coma remains smooth and bright, not ragged or chaotic as you'd expect if it were breaking apart. The contradiction is stark. The comet is losing mass at a catastrophic rate, yet it shows no signs of self-destruction. The surface area problem remains unsolved. Spectroscopic data from JWST and Hubble in mid-2025 forced another confrontation. The gas streaming from 3I Atlas wasn't just the usual suspects. When astronomers analyzed how sunlight scattered off the comet's coma, they found a level of negative polarization more intense than any comet on record. This signature is reminiscent of icy bodies from the far edge of our solar system, implying a mix of dark and icy grains unlike what's typically observed. Mainstream comet scientists acknowledge these values are unusual. They argue that interstellar visitors should be expected to surprise us. With only 2 previous interstellar comets to compare, the sample size is simply too small to define what's truly abnormal. But this debate won't stay theoretical for long. On March 16, 2026, 3I Atlas will sweep past Jupiter at a distance almost exactly matching the planet S-Hill radius, the region where Jupiter's gravity dominates. This encounter is being hailed as a natural experiment. If the comet's trajectory or activity changes in ways standard physics can't explain, or if its chemical emissions shift dramatically, the data will provide a decisive test. As new data pours in, each unanswered question pushes the limits of what we call normal in our universe. Sometimes the rules we trust most are the ones most urgently in need of rewriting. What do you think this object is? Let me know in the comments. Thanks for watching.